Start, sir.
Hello, welcome to live session 3 of Plant Design and Economics. A very good afternoon to all of you. So today we'll talk about a case study related to chemical process safety. Basically, we'll analyze an accident that happened way back in 1974 and which changed the way safety is practiced in chemical process industries. In particular, we'll talk about Flixborough accident. The chemical process industry expanded rapidly during 1960s. But then three major accidents happened in a span of 10 years. The first major accident happened in UK, England, at Flixborough, 1974. Then another accident happened in Italy, Seveso, in 1976. And in 1984, the largest ever accident happened in chemical process industry so far happened in Bhopal, Madhya Pradesh, in our own country, India. We have discussed and analyzed to some extent about the Bhopal gas disasters when we talked about chemical process safety as a regular module in this course. So today we'll talk about the Flixborough accident, which happened in 1974. The process safety in chemical process industry gained serious attention internationally after the Flixborough disaster that witnessed a catastrophic explosion causing major loss to life and property in the United Kingdom in 1974. In 1984, the Bhopal toxic gas release incident caused by a runaway reaction was unprecedented in the history of chemical process industry. Several thousand people were killed and several lakhs of people were affected. Now it is important that we analyze such case studies. The study of these case histories gives us valuable information about process safety. We can use this information to improve the procedures in process industry, the operations, the handling of events, such that similar accidents can be prevented in future. Because of these incidents that we talked about, chemical engineering profession has now added new emphasis and standards in the practice of safety. As we just discussed, the Flixborough accident is the largest single loss by fire or explosion ever experienced by the United Kingdom. It happened at Nipro factory at Flixborough in the United Kingdom. What was the reason of this? We'll go through the reason more detail, but right now, in a single sentence, if I have to say, I'll say that the accident happened because of a temporary pipe installation that was done in a very unprofessional way. So that was an unwise planned maintenance modification. We'll just discuss what that modification was, but it was a very simple modification which required a temporary pipe installation. However, this temporary pipe installation was not so easy because the operations involved high temperature, high pressure. However, this temporary pipe installation was not done properly, was done very unprofessionally, and the temporary pipe failed or ruptured 2 months later after it was installed. The plant was using cyclohexane. When the temporary installed pipe failed, it caused the release of about 50 tons of hot cyclohexane. The cyclohexane mixed with the air and exploded, killing 28 people and destroyed the entire plant. A total of 28 individuals lost their lives. Out of 28 fatalities, 18 were found in the control room. 36 employees experienced injuries. 53 non-employees had recorded injuries. The estimated property damage was of the order of 63 million US dollar, estimated in 1976. There was so much fire that even after 10 days, the fires were hindering rescue activities. So here are some disturbing photographs of the after effects of those fires and explosion at Flixborough. Now let's look at the process in a little bit more detail. So what was the process? The Flixborough Works of Nipro Limited was designed to produce 70,000 tons per year of caprolactam. The caprolactam is a basic raw material that is used for the production of nylon 6. Now this cyclohexane that was used for the production of caprolactam is not very easy material to handle. It has properties similar to gasoline. Its vapor, when mixed with air, will produce an explosive mixture. And the process that was followed at Flixborough was at a temperature of about 155 degrees Celsius and almost about 8 atmospheric pressure. Now, from this high pressure and high temperature, when this cyclohexane leaked, it volatilized immediately because it depressurized to atmospheric conditions. This is the reaction that was followed. You first do hydrogenation of benzene to produce cyclohexane, and cyclohexane is oxidized by using air to produce cyclohexanol and cyclohexanone. So ketone and alcohol. This is also known as ketone alcohol mixture, Ka mixture. Now caprolactam can be produced from this cyclohexanone. So benzene is treated with hydrogen to produce cyclohexane, and the cyclohexane is oxidized using air to produce ketone alcohol mixture, that is cyclohexanol and cyclohexanone. Cyclohexanone is then used to produce caprolactam. So mixture of cyclohexanone and cyclohexanol, usually known as ketone alcohol mixture, was produced by the oxidation of cyclohexane by air injection in the presence of a catalyst. So that was the process. Now this is a simplified flow diagram for the cyclohexane oxidation plant that was there in the Flixborough plant. Note that there were 6 reactors in series. You can look at here, number 1, then number 2, 3, 4, 5, and 6. If you also look at each reactor was slightly lower than the one before. It was done such that the liquid can flow from one reactor to the other, from the first reactor to the second reactor, from second reactor to the third reactor, and so on and so forth, due to gravity. And these reactors were connected in series by short 20-inch diameter connecting pipes. To allow for expansion, each 20-inch pipe diameter contained a bellows. Bellows is an expansion joint. So this like is expansion bellow. So you can also notice that there is provision for air injection to each reactor. Air is required for oxidation of cyclohexane. Now, the product from the cyclohexane after oxidation will be ketone alcohol mixture, cyclohexanol and cyclohexane. But the reactor still contain about 94% of the cyclohexane. So, in the subsequent stages, the reaction product will be distilled to separate the unreacted cyclohexane, and then it will be recycled to the reactor number 1. So a lot of cyclohexane would be recycled. So here you can see more clearly the bellows. And this is the connecting pipe. Now the accident happened in June 1, 1974, which was a Saturday. And it is said that the casualty was less because it was Saturday, not a regular office day. Otherwise, more office personnel would have been killed. Now, before the explosion on March 27, 1974, that means about 2 months back, it was discovered that a vertical crack in reactor number 5 was leaking cyclohexane. So 2 months before the accident happened, a vertical crack in the reactor 5 was noticed. So an investigation was carried out, and the investigators identified a serious problem with the reactor. So they decided to remove reactor number 5. But then they also decided to connect reactor 4 with to reactor 6. So they basically installed a bypass assembly to connect reactor 4 to reactor 6. So reactor 5 was bypassed. A bypass assembly was used to connect reactor 4 and reactor 6 so that the production can continue. But the problem is this bypass pipe was not properly supported. And because there was bellows at each end, note that there are bellows at both ends of the connecting pipes, that is connecting to reactors. So the bypass pipe has bellows at each end. Now, since it had bellows at both the ends, it was free to rotate. And it rotated when the pressure rose a little above the normal level and the bellows failed. So the bypass assembly was ruptured. So this happened during the late afternoon of June 1, 1974. This resulted in escape of a large quantity of cyclohexane. The cyclohexane formed a flammable mixture and then subsequently found a source of ignition. It is not exactly known what was the actual source of that ignition, but since there was formation of large flammable mixture, it found a source of ignition, and at about 5 p.m., just 7 minutes before 5 p.m., there was a massive vapor cloud explosion, which caused extensive damage and started numerous fire on the site. It killed 28 people, destroyed the entire plant, and the fire was so severe that even after 10 days, the rescue operation was hindered. So note that how a temporary modification that was not done professionally killed so many lives and destroyed the entire plant. No professionally qualified engineer was there in the plant at the time of the temporary pipe when the temporary pipe was built. The man who designed and built the temporary assembly did not know how to design large pipes required to operate at high temperature and high pressures. But it is true that designing large pipes or such bypass assemblies which will be operating at high temperature and high pressure is not so easy, because your pipe will be under highly stressed condition because of high temperature and pressure. So designing highly stressed piping requires specialized knowledge. But the problem at the Flixborough was that their engineers even didn't know that the design required experts. So the persons who built the assembly didn't have actually any professional knowledge. And the personnels working at the plant site even didn't know that this problem has to be addressed by experts who have specialized knowledge about designing bypass assembly, which will be operating at high temperature and high pressure. Now, we ask the question, could the accident be avoided? The answer is yes. This accident could have been prevented by following proper safety procedures. First, the bypass line was installed without a safety review or adequate supervision by experienced engineering personnel. In fact, it is not appropriate to say that the bypass assembly was designed. It was not a design at all. The bypass was sketched on the floor of the machine shop using a chalk. So no design formalism was adopted, because they didn't know that the service of experts required here. The plant site contained excessively large inventories of dangerous compounds. You have also seen this problem with Bhopal gas tragedy. Large amount of dangerous inventory should always be avoided. At Flixborough site, they stored 330,000 gallons of cyclohexane, 66,000 gallons of naphtha, 11,000 gallons of toluene, 26,400 gallons of benzene, and 450 gallons of gasoline. So these large inventories or dangerous compounds, these large inventories of dangerous compounds contributed to the continued fire that happened several days after the blast. And that hindered rescue operation even 10 days after the accident. So the magnitude of the fire and explosion, magnitude of the fire at least could have been minimized if there was not so much of inventories of dangerous compounds. Finally, The bypass modification was substandard in design. As a rule, any modifications in the plant should be of the same quality as the construction of the remainder of the plant. So these strategies, if adopted properly, the Flixborough accident could have been avoided. So these two strategies that we talked about here are mainly proper design and proper safety review of any modification that is required at the plant site. That is number one. And second is, we must avoid large inventories of dangerous compounds. Now, see, another possible way of avoiding this accident altogether would have been use of a different chemistry to produce caprolactam, which is, as an important intermediate for nylon 6. What is that? Before the accident happened, the Flixborough produced caprolactam by producing cyclohexane. So benzene was treated with hydrogen to produce cyclohexane, and then cyclohexane was oxidized in presence of catalyst to produce cyclohexanol and cyclohexanone, ketone alcohol mixture, and then caprolactam was produced from cyclohexanone. So that was the strategy used or the reaction route used before the accident happened. So that reaction path involved the dangerous compound cyclohexane. Now, another route can be through hydrogenation of phenol. So here, what can be done is ketone alcohol mixture can also be manufactured by hydrogenation of phenol. So benzene and propene are reacted to produce cumene. And then cumene is oxidized. So by injecting air, so cumene is oxidized to produce phenol. And we can also produce caprolactam for phenol. And if you want to produce the ketone alcohol mixture, so you have phenol can be hydrogenated to produce cyclohexanone. So a different reaction route can be used, which involves hydrogenation of phenol to produce caprolactam. So benzene and propene are reacted to produce cumene, and cumene is oxidized to produce phenol. So benzene plus propene will undergo reactions under catalyst to give you cumene, and then cumene will be oxidized to give you phenol, and the phenol can be used to produce caprolactam. So this was widely publicized that it is an inherently safer route. And after the accident at Flixborough in 1974, when later they again rebuilt the plant, they actually adopted this inherently safer route, much safer route compared to the previous reaction route. So we have also seen that in case of Bhopal gas tragedy, there was also an alternate route, and the production of that intermediate methyl isocyanate could have been avoided. So it is very important that we minimize the inventories, large inventories of dangerous compounds. We take appropriate care and safety review. We do safety review before we make any temporary modifications on the plant site. And always look for inherently safer route or reaction pathways to produce intermediates or the final products. That will lead to inherently safer chemical process industries. So with this, we'll come to end of this live session 3. And before we end, once again, a reminder, the date and time of the examinations for plant design and economics. The exam date is December 20, 2020. Exam will be held in 2 sessions. Morning will run from 9 a.m. to 12 noon. And the afternoon session will be between 2 p.m. to 5 p.m. And as you know, the type of examination will be online. If you are writing this exam, I wish you all the best. And thank you for joining this course. Good luck.
Done, sir.